So welcome to this year's Vectorizer BOF. So like every year, we're trying to shortly present what happened in the last year to the Vectorizer and then open up for general questions and concerns about vectorization. So I want to give you a short update to what happened in the Vectorizer. It's a very short update because like last year was mostly from my side. I probably missed all the work from others on getting the transition to the SLP only. I called it in the last times I talked about this topic for the Vectorizer. That means that we are using the SLP data structure for all vectorization in the Vectorizer. So previously we had the statement info only view for the classical non-superword parallelism vectorization parts in the loop, plus in case you had superword level parallelism SLP data structures, and basically everything was implemented twice, once on one data structure, once on the other, and that's of course, well, it creates friction. And so finally, I think after 6 or 7 years trying to get it through, so we did it. So we released GCC 15, and there's a param that switches that mode on, and it's on by default. And for GCC 16, I think we've now removed most traces of this code sharing, and so we are only having the SLP data structure operation left. So now it's no way back, basically. The other thing we did for GCC 15 that's very user visible is that the O2 vectorization we do now allows for epilogue peeling. That means when you have a non-constant number of iterations or a constant number of iterations that doesn't exactly divide by the vector size, you can get vectorization at O2. So previously for code size reason, we didn't consider that appropriate for O2, but now we do. And like if you look at spec, that makes a big difference because usually you don't know the number of iterations of a loop. Right? That's the very usual case. And it comes indeed at like 10% code size increase for spec SP, which has many vectorized loops. So we took that thing to make it was really inconsistent what kind of loops you got vectorized at O2. And I think it makes sense what we do now. So we still don't do versioning and prologue peeling or epilogue vectorization at O2 by default. The other thing for GCC 15 is that we made early break vectorization more applicable to also general code. Like in GCC 14, when we introduced that, it was restricted to the cases where GCC could statically decide that doing overreads on memory was never going to be a problem, but it's not going to trap and whatever. And with GCC 15, we are now guaranteeing this by means of doing alignment peeling, so basically using alignment as the guarantee that it's not going to be a problem. And that makes it much more applicable to real-world code. So previously, basically, it only worked when you operated on declaration directly, so never when it was pointer indirect. So then we will now do a short update on what happened architecture specifically. I will cover x86. So with x86, the GCC 15 now can do multiple vector epilogues. So like if you have a loop that's vectorized using AVX 512, you can get a first vectorized epilogue with AVX2 and a second vectorized epilogue with SSE. It's not enabled for the other architecture, so it's controlled by the target hook that basically tells the vectorizer, maybe I want some other vectorized epilogue. Because the other ISAs don't have these multiple sizes. They have variable lengths and fixed lengths, but not different fixed lengths.
Yeah.
Or maybe, so they didn't decide to opt in yet.
No, it actually does it for some reason. I've seen it on AR64. I've actually seen the AR64 epilogue being vectorized. I don't know.
Yeah, sure. But did you see two? So the epilogue of the vectorized epilogue.
Oh, okay. No,
You know.
because there's only 2 sizes, period.
Right. So
Not 3.
we have 3 with x86.
Yeah.
And the other thing is that on the AMD Zen, which has AVX 512, it's actually profitable to instead use a masked epilogue. And we now do that by default. If in some specific circumstances and in some not, so there's some target-specific magic there. I don't exactly remember, but so the issue is usually that you need to avoid store-to-load forward issues, because usually the masked stores do not forward to masked loads. And there is, I think, 2 cases in Spec 2017 where if you don't, when you are not careful, you absolutely run into the situation and your performance is going to tank. So that's now done by default for GCC 16 on select loops and on Zen at the moment. So I didn't do any benchmarking on the Intel server architectures. I guess Intel folks will eventually do that and decide whether it's profitable for them or not. And on x86, we have the very many vector sizes. So with AVX, you have the issue when you have permutes, and you have your microarchitecture cannot do the 256 width, but it internally splits into 2 halves, and you have the permutes that cross these 2 halves. They are very slow because they kind of fall back to microcode or whatever. And so we did cost model improvements there. So previously we said, oh, all permutes are bad. But there are, of course, in-lane permutes, and we now better detect those and basically do more vectorization when you tune for these microarchitecture. That's apparently most important for the Intel small core server things. I think it's called Sierra Forest style. So they only can do the 128-bit with data paths, but they have AVX2 at least. So next one is Tamar. So I'm supposed to hand over the. Oh yeah, you can use that one.
Yeah. So for I forgot to put an update on GC 15, so I'll give it orally. So last year we mostly focused on VLA vector calls for math functions. So we're now able to support something like cosine or something using an SVE call. We're still trying to figure out the best way to get profitability here. The ABI has some issues around copying around the predicate. And I think the best way for us to solve that is to support unrolling of vector math routines, which we'll cover in the AR64 BOF. But for what we're working on, more peeling for alignment. So as you mentioned, last year we added peeling for alignment for VLS, but not VLA. For VLA, the problem is, well, what if you have a very long vector length? You might be peeling for a lot of iterations. And so instead, we peel with masking now. So that's in GC 16. And we also support mutual peeling for alignment. So if you normally peeling for alignment could only be done for one source, but now if both of them are mutually misaligned, you could peel to alignment. This does introduce some complexity with VLA because we rely on alignment, but your vector loads could be so large that you couldn't just cross a page boundary every iteration. So we have to do a page size check before we enter the vector loop. So the prologue is a bit more complicated and expensive. To fix that, we want to use first faulting loads. That's basically a way for the ISA to basically collect faults along the way and tell you at the end that you can load X number of elements without any issue. So that's ongoing work. We've enabled now enough of early break that we're getting quite a lot of reports on them saying, well, it became slower. So we're spending a lot of time analyzing the code, and the majority of the problems are twofold. One, again, for SVE or even for Neon sometimes when we unroll, you spend a lot of time in the prologue and in the epilogue. At the moment, when you find an element, you have to branch out to a scalar loop to actually do the side effects and actually find the element index. But you can imagine that, for instance, the element is in the first iteration. You've done a vector iteration. Now you redo the entire work on scalar. So it's essentially just twice as slow as before. And so to fix that, we have to stay within the vector loop and handle everything within the vector loop itself. Turns out the design we had was actually pretty good. So I can incrementally change it to support more things as I go along, and most of the patches are quite small. So I'm hoping to send them up next week or so, at least the first parts. And then we're looking more into general control flow. So what if you have an end-end expression? Or if you have an if-else expression inside the vector code? We want to be able to vectorize stuff like that as well. One of the restrictions we have for early break today that is one of the exits must be counted. We don't care which exit, but one of them must be counted. We are trying to relax that now and to say you can even vectorize if you can't count any of the exits. So something like if C and C is a pointer and you load it every vector iteration, you have no idea when you're going to stop iterating. That is quite far along. We can generate the code, but then we're fighting at the moment with stuff like alias analysis and cost modeling, stuff like that. But hopefully we'll send it up soon as well. One of the other big topics, not for GC16, but probably 17, is revectorization. That is treating vector code as scalar elements for the loop vectorizer. So that means you can resize, for instance, code written with intrinsics, or even change ISA. So one of the new things in SVE is that we're introducing a new hybrid VLA mode. So now we'll have to pick between 3 different vectorization modes, essentially. And for that, we want to teach a vectorizer to be able to understand existing vector code.
Okay, so I'm going to talk a bit about RISC-V. That's somewhat longer because there hasn't been any update on the RISC-V vectorization so far. So I also included like GCC like possibility was added. And one particular thing is we needed to add our like loop control idiom select VL to the vectorizer, which helps us create more efficient code and also makes it much easier to support down counting loops in the vectorizer. The rest of the like topics was as we are late to the game. Like we first needed to make sure we don't do stupid things before we get them fast. So one thing that was missing for us was that for AH64, mask loads implicitly zero out the inactive elements, or any other architecture, as far as I know. For us, it's not so easy, because it's basically unknown what is being produced by inactive elements. So we introduced an explicit else operand for masked vector loads, which helps the vectorizer generate an explicit zero if it needs to. It's very rare that it needs to, but in those cases where it needs to, the code would be wrong otherwise. Then Panli has added, that went into GCC 15. And for now, what's happening in 16 is Panli has added a lot of saturating arithmetic, because we have like a bit of scalar support for saturating arithmetic, but also a lot of vector support there. And that's pretty involves a lot of match PD patterns, so we're quite far along with that. And another thing is, like that on RISC-V, at least so far, what seems to be apparent is that gather, scatter, and strided loads, which are actually all the same, are not as bad as on like older architectures, let's say early x86 or so. So we want to support them as first-class citizens, basically, in particular the strided loads. But what was missing is an alignment check in the vectorizer, because like so far the assumption was like these are all under the hood, these are scalar loads basically, and we don't need to care about alignment that much. On x86, on RISC-V, not on x86, on RISC-V, we actually mandate in the spec that a vector must potentially be element aligned in order to not trap. So it's really disastrous if we didn't check for alignment. So that's happening now. What's cooking is basically, and what we have been battling out a bit during the last some weeks, is gather scatter with type punning. So like for this loop there, that's kind of straight out of x264, we load 4 character elements, so 8-bit, and they're like successive in memory. But what we could do instead is load a single int. And this, in turn, in combination with that loop, would allow us to generate one strided load with 4 ints, which is obviously much more efficient, at least on our microarchitecture, than loading it individually as, like, I don't know, 4 or 8 vectors of characters. And this, here it becomes apparent where we need to gather and strided access, because that's basically all the same. And what also plays into this is we want less strict gather-scatter discovery early on, because it just helps us to like cost things that we do in the back end easier. And yeah, I'm not sure if this will still make it into GCC 16. I guess I need to step up my game a bit, and then let's see. But it's actually not a big change, and yeah, I guess that's it so far for RISC-V.
So that was basically the idea, to give you an update. Now we would like open up for your questions. We do have a lot of backup slides in case we have to discuss amongst our 3. But please, Andrew.
So this isn't exactly vectorization, but vector bools from a C point of view, how do we do them, and is that on anybody's radar?
I think there's the libstandard C++ SIMD guy. I think he's not here, right? Who is basically trying to use less intrinsics and more general vector extension to implement the C++ SIMD extension. But the difficult thing about the vector bools is that they are target specific, right? When you have vector data, I mean, it's clearly that applications know how they lay out data in memory, and they can do a vector load of that. But when you expose something like a vector bool out of a computation, and an application wants to store that somewhere, that storage representation is target specific, right? So for the libstandard C++, it's ISA specific, so not even only target specific. Like on x86, we have 2 different representations. There's no ABI for that in general. The ABI doesn't talk about passing a vector bool, because like on x86, all the intrinsics either represent them as vector data or as integer data, right? But internally, those are vector bools. So currently, the vector extension doesn't expose them. So as soon as you produce them, they basically decay, like a character decays to int, they decay to data. They decay to a vector of -1 or 0, to a data vector. And I think that's very reasonable. And so the question is always, but the code doesn't get optimized. And I think because we do that, and I guess we just have to get better optimizing that. I'm not sure whether we really should expose those vector bool thing, because, well, you get into all these ABI and whatever issues and compatibility with other compilers, and it's going to be a mess.
So as a user of Vectorizer, so when we looked at the programs, like we wanted to look at certain loops which are hot, and then we wanted to force them to certain vector sizes and see the performance, but we are not able to do. So is there any pragma or a way to do an individual loop and force it to vectorize to certain size?
Yes.
That works. But that works with dash OpenMP,
but
right?
you get the SIMD handling of the loop. So no, there's no pragma to direct the vectorizer or do special things to a specific loop. But we have the pragma to not vectorize a loop.
But can that be added? It will be useful.
So
Then the question is if it's a preference or a requirement.
yeah. So usually my question is then, did you check what other compilers do? Does that work? Then we can adopt that. So inventing something new is always the least resort, but I can see that it might be useful.
Yeah, we've discussed it before as well.
You have to pass the mic.
Yeah, so we've discussed this before as well, because a lot of times we can't just disable the cost model for the entire program because everything will become slower, and you just want to see on a particular loop. So at least for in the mid-end this year, I added something to override scalar costing. So they'll tell it to, it should be profitable to vectorize, but keep the inner vector mode comparison active. So the compiler will still try to figure out the best mode for it. What we don't have yet is a way to specify which mode to use. Internally, when we last discussed this, we thought modes might not be the best way to go, but instead allow you to specify the vectorization factor. And that would limit the modes you get out of it. And that would be a bit more general. Now, unfortunately, the generic part to enable or control scalar costing is a parameter, so you can't really set it per loop. But on the AS64 backend, for instance, we did create a option that allows you to override it on a particular loop.
Yeah, so a little bit related is your work on the interpretation of the unroll pragma we have when the vectorizer comes and unrolls a loop. So like when the user requests unrolling by 4, does he maybe request vectorization with the vectorization factor 4? Or when we vectorize, does he still want us to unroll the vector loop by 4? And so Tamar tried to kind of reinterpret what we do to the unrolling when we vectorize. So we could also take that as a hint for the vectorization factor, but only as a hint, I guess, because otherwise it would likely regress.
It's actually giving a flexibility, right? So not all, for example, if you take x86, not all these servers are 512 bit data path enabled. Some of the variants have 256 data path enabled. So when you use MH equal to Zen 5 or Zen 6, it can't really pick up which one is good. Basically, there are two SKUs now, one with 256 data path and one with 512 data path. So the costing cannot be generic across these two variants. So there has to be some flexibility for us to decide, or at least to check out which one would be better. And based on that, probably we can take a choice between which one to take. But I understand that there is a need for mode, but this would also help us in giving a flexibility to check how it performs, especially for a loop of interest.
Yeah, so I think it might be a possibility to complement the OpenMP SIMD-LEN pragma to also be like parsed and put somewhere and used by the vectorizer, even if you don't use dash of OpenMP SIMD. I'm not sure if that's a way, or if you should create a different pragma.
It wasn't meant to be the option to use if you don't put one with full OpenMP.
Yeah.
LLVM also has something called force vector width. That is at file level. But obviously we can take out that particular loop or function and put it in a file and check it out. So I think one option which enforces the vector factor would be helpful.
Yeah, I think it's also a general thing about other loop optimizations we have. Like, what controls do we have for the user to per loop to influence what GCC thinks is a good transform? Because it's often just a guess, and sometimes it's a bad guess. So like we have the no vector thing. Maybe we should have other controls. And as I said, we need to research what other compilers do to not add to the confusion of different pragmas that might be out there, and basically learn from their mistakes.
But the OpenMP SIMD has two major clauses for the vectorization. One is the safe len. So how many iterations don't have the forward dependencies? Because IVDEP is infinity, but in OpenMP you could perhaps specify something lower, but we probably don't handle it well. We just handle either infinity or nothing. And the other is the SIMD-len, which is the preferred vectorization factor.
So we are using the safe len in the vectorizer, but I don't think we are using the SIMD len because that's not recorded.
I think we record both, and
it's both
I think we
recorded.
start with that vectorization factor, but I could be wrong.
Yeah.
At least it was meant to be that way.
Yeah. So the issue is we're not iterating over vectorization factors, but we are iterating over modes. So it's not the same, right? So it's not easy to say, well, yeah, start with vectorization factor 4 and now vectorize, because we have to start with AVX2. So I would suggest, please open a bug report.
So another thing we noticed in early break vectorization is like when the program breaks from the vector part of the loop, it repeats the last iteration. So I understand it is for side effects, but like if program doesn't have side effects, still it does. So we have some, x86 has some instructions like tz count, pop count, where you can figure out where it broke. Then we can resume the scalar loop from that point. Is it some work going on there?
So maybe you want to show the slides you have on that topic. If that helps.
Yeah. So, so as you mentioned, so the main reason we started with going to the scalar code, it was actually the harder path to take, but it allows us to vectorize loops like this. So for instance, on assert will no longer block vectorization. These two cases, for instance, aren't one you can ever handle by staying inside of a vector loop. But you're right, in a lot of cases, you don't have these kinds of side effects. So you should be able to handle it. So I already mentioned in first faulting loads, this is for, in order for you not to have the long prologue for alignment peeling. This one, as I mentioned before, it has quite a bit of issues at the moment. So for instance, because we also expose it as intrinsics, we have to make sure that if we vectorize a loop that's part of some in-between intrinsic calls, that one intrinsic didn't start a first faulting load and then try to use the result afterwards because we would clobber it in between. Or like if we're doing inner loop vectorization, that the outer loop doesn't have any uses of it. So there's a lot of data flow analysis that we have to do before we even start to vectorize. It's also about like representing the loads. So I was telling Richie that we have normal loads from first faulting and non-faulting, and we have them for every individual type of load that we have in SV. So we can't really keep generating op-tabs until the functions here. It's just never going to end. And we have the issue that the MMU can give you basically an unnecessary fault. It can tell you, hey, I don't have any data for you at the moment, come back later to give it time to go prefetch it. So we have to handle those cases where you just have to restart the loop again. So, and at the moment, the difficulty is that we can't introduce new control flow in the vectorizer. The vector code must match the control flow of the scalar code. So it kind of limits us, but we're working on lifting those restrictions. I'll skip to what you asked for. So, for instance, this function, you don't actually need the scalar trail because the return value is invariant. You have nothing to search for, and there are no side effects. To enable the second cochain, it's actually a two-line change in the vectorizer. So that was the first thing I started with. Essentially, it just tells us we have a list of whether you have side effects. We have a list of whether you have any reductions. If those two are false, you don't need the scalar loop. The next part becomes a bit trickier. So when you're doing index reduction, so like a return I, in that case, the ISA needs to provide us a way to partition the mask. We need to know the part before the first true part in your comparison. So for that, we're introducing a bunch of new internal functions. So for instance, give me all the active links before the first one, give me all the active links including the first one, and then introducing a new op-tab count active. Now whether you expand it to pop count or whatever, that's up to the target. Right, and so in this case, with these two in place, we can generate the second code where you again don't have to go to the scalar code. The third easy case is when you have a data reduction. In this case, we don't need to partition the mask. We just need to provide us a way to get the first active element in the comparison. So we're introducing a new op-tab, extract first. Although I think we were talking about if we can reuse extract last and flip the predicate, but we'll figure it out. But essentially, you can get in SV, you have compact. In AVX, you have VP compress. I think RISC-V also has similar instructions. So as long as you provide the op-tabs, it should all work for the simple cases. After this, it gets a bit harder. So if you have a store, the problem with the store is if you take the exit, we still have to perform the partial iterations on the partial stores. And so in order for us to do that, we need to be able to duplicate the store. The problem is at the moment we just move the store. And we can only move it into one place. And so we've tried before, we tried to vectorize, we tried to move the stores after vectorization. That is hard because GDC generates a lot of different store types after vectorization, while on scalar it's just a simple assignment. Now we're moving it before vectorization, but then the problem there is I can't move it to 2 blocks. And it also breaks epilogue peeling. So what I'm trying now is to move it during vectorization itself. So we just materialize it in multiple blocks. And that should work and also give us back epilogue peeling. The difficulty is here I have to figure out a new way to update the v-uses chain. It's not hard, but it's a bit cumbersome, especially if you have more than one exit. This one shouldn't need any new target capability aside from the mask partitioning again. So I also have this one working, but not entirely happy with it, but I'll come back to that. What's difficult is if that return statement has more statements, because then it means that the vectorizer must if convert the statements on the fly. And that's the part that I'm punting for 16. I'm not even going to attempt it for now. Right, and then the last step is, you've probably noticed that in some loops, you get now 3 vector IVs. You get an upward counting one, a downward counting one, and a scalar one. This happens because for the current implementation we have, when we find any IVs, we force them live because we need them for the scalar code. And then what happens is that IV canon introduces, when it sees a IV of a known count, it introduces a downward counting one for do loops and for IV ops. And it's to give IV ops the possibility to choose a different IV for cheap addressing mode. And it expects IV op to be able to clean up the duplicates. However, IV ops doesn't understand vector IVs, so it just leaves them. And so you end up with the 3 reductions. To fix this, instead of having the vectorizer generate a vector IV, it generates a new scalar IV that does this vector offsets. And so that allows us to clean up the code from the first part to the other, and so you drop quite a few instructions. So those are the kind of the things that hopefully we can still get into 16. All the changes are actually quite small. So most of them are maybe 2 or 3 lines. The most difficult one is moving the stores.
So I'm interested in the topic of revectorization, and in particular, the case where you have user code written with, let's say, fixed with neon intrinsics, and you might want the compiler to automatically scale to wider SV in the future. So I mean, if the intrinsic is folded early on into standard Gimple, then that's fine, just Gimple stuff. But for those that aren't going to have the Gimple code because they're like very specialized operations, do we see introducing? Do we expect we'll teach the backends to have some kind of translation hook where they translate the internal built-in from one ISA from the Neon to the SV ISA, or how would that work?
So I think there's two things. One is that we get two opinions on intrinsics in general. One is the compiler shouldn't touch intrinsics. I've written them. I want exactly that. So what's the point in even thinking about re-vectorizing to different intrinsics? That's even worse than, right, for those people. So we probably need to control this somehow, which also means control whether you lower the intrinsics to Gimple or not, right, for that case. And then for the second thing, so when there is intrinsics that cannot be, that are not be lowered to Gimple, I would kind of postpone that to the point where the vectorizer can deal with vector code. So my plan is, so currently we have the vectorizer, and then we have the vector extension in C and in C++, and we have intrinsics on several targets that get lowered to Gimple, right? And we have the vector lowering pass, which looks at each Gimple statement and decides, can the ISA handle that? And if not, it blows it away and does something that is handled. In the worst case, it outputs scalar code. And I want to have the vectorizer do that. Basically, always think of vector lowering as re-vectorization if it's also outputting scalar code, right? Because that would us also enable to like handle partial vectorization in the vectorizer. Like if you have a loop with a call, then we can just emit four calls to scalar code for a vector data input. So I would like to go into that direction, but Tamar already worked on like making the vectorizer understand the Gimple vector code in the first place, like put it into the data structures that are used for vectorization. And I guess I'm expecting we have to fight a little bit on the data representation, but that's the first step. And then the rest should magically, hopefully, appear.
Well, so like Reggie said, then for the next release, I'm mostly focusing on how to get the data representation right. There are a hell of a lot of problems with this. For instance, reductions. How do you recognize a reduction from an intrinsics? The problem with permutes, because SV and Neon permute data differently, top bottom versus even odd. So if you want to change between ISA, you need to be able to understand the data flow and convert them. So for now, my plan is to look at stuff that have been lowered, then look at stuff where the instructions don't change. So addition, for instance, is the same thing between the two. And then the permutes become the difficult part. One of my main motivations for doing this is because there's a lot of old code written for old microarchitecture. We have a lot wider vector units these days, so you can benefit from unrolling, you can benefit from epilogue generations and stuff like that. The switching of the ISA, I think, will be a cost modeling issue in the end. But yeah, it's a difficult problem, especially how we've modeled intrinsics in GC. I think at the end, so what I was playing around with is providing somewhat annotations like we do for the math routines. You say for this built-in intrinsics, we have these different variants, and then it's up to the backends to generate and provide them. And then it means that you can just handle them as a normal function call. We just generate this wrapper essentially, and then you unwrap it in the backend on expansion.
Like if you had OpenMP SIMD
exactly.
Attributes on your intrinsics,
exactly.
And then magically select the correct one, yeah.
I'm just thinking from with my ARX4 maintainer in the hat is like we have a bit of time, G16, G17, where we could I would like at some point to transition the intrinsics to not have them in the one arm.h header needs to be reparsed, right? And we do the same way we do the SV intrinsics, where just a pragma and the compiler just injects the right IR, right? And there we could annotate whatever, we'd add whatever attribute we want, internal or as boutique as it needs to be. So basically, if we kind of can decide or have some indication of what the approach there, we could kind of start, prefetching that work a bit now, because we will need to do that transition anyway for other reasons besides the revectorization. So we could get the intrinsics backend part potentially into shape sooner than the vectorizer gets all that complex stuff sorted out.
So one other possibility, rather than like mapping intrinsic to intrinsic, would be to give the target the ability to decompose the intrinsic into Gimpel code just for the vectorizer. So like have a pattern.
Yeah, the problem with that. So the problem with that is, and the reason I didn't want to go down that way is SVE has quite a few instructions, and every single year we add hundreds more. And so even if you want to introduce some kind of Gimpel representation for it, we still have to add a lot of overhead in Gimpel, I think.
So you say that there are instructions where there is no Gimpel representation for the semantics? I mean, multiple statements, possibly?
No, well, a lot of them you would have to lower as IFNs. So for instance, the complex number instructions are one, matrix multiplies, a lot of those more esoteric instructions. So
yeah, you would lower them to the appropriate SLP tree with the permutes and operations and. So and then you pattern match them again if the target ISR has them. Yeah, right.
Yeah, but then we have to extend the 3-effect SLP with a lot of pattern matches.
Well, it would all in the target because only the target needs.
It's possible.
So I was just throwing in as a different possibility to handle some of the intrinsics, maybe.
Well, the other issue is that because a lot of especially the loop control statements, we have a problem with getting SCAF to know how the iteration for certain loops. Like for instance, for SVE, the while low is in the header itself.
Yeah, I can see it's going to be very difficult to revectorize variable length intrinsics code, but I also wonder if that's a good target to pick, because you're talking about revectorizing out like neon code and not as modern SVE code yet.
Yeah.
Yeah. So let's go there when we have to get there.
Well, yeah, because for my use case for SVE is that we could generate a neon main loop and an SVE trail for it. So there are cases still where you want to go the other direction, just because the most microarchitectures have more SIMD units than SVE. SVE has throughput limitations on some instructions. So.
So that's also like, in principle, the loop unroller would also be a candidate for SVE loops with intrinsics, which would need to understand the looping. So it's not a vectorizer only problem. Once you try to optimize intrinsics code, you either make the user very unhappy or you're making the compiler unhappy, basically.
I mean, for the user, we have pragma no vector.
Yeah.
So you told about the stores that are getting generated during this early exits, right? Where to exactly move. So how is the costing done for that? What challenges it posed on costing aspect of the vectorizer?
So for for the stores themselves, it's not much of an issue. We just cost them as the vector trail, so the vector epilogue. So the vectorizer. So if you look at the vectorization structure, you have cost for the loop body, the loop header, and the loop epilogue, and we have them for the scalar as well. Essentially, when you move the vector code, At the moment, because we move it before vectorization, it's costed in the right location. When I change it to move it during vectorization itself, I issue an explicit costing saying I have moved this outside of the loop, so the variable you get isn't vec body, but vec prolog, for instance. What's really difficult for costing for us is that SVE and Neon doesn't have the same throughput for, like, say, compare instructions. And this changes the code gen that you want between these two. What's also difficult is that SVE provides a way to branch based on the condition code of the resulting vector compare, where Neon doesn't have it. So you have to account for the reduction steps that Neon has to do. If you're going to unroll, SVE doesn't require you to have an OR in between to combine the mask. You can just branch on the mask, on the compare just directly. So these kind of things influence our costing a lot. So that's why for maybe 16, I'm not sure, probably 17, we will change our cost structures again. At the moment, we only model throughputs based on issue rates for data and predicates, but we're going to narrow it, model throughput based on specific instruction types. So like compares, generic ALUs, shifts, etc. We'll get now different modeling.
So that's quite target specific. So that's ARM, and on x86 we are not even letting the vectorizer compare like AVX512 to AVX2 vectorized code. We are just picking the largest one or the one we start with when the vectorizer figures, yeah, we can vectorize and it's profitable. So we only have not profitable, and we go on to the next vector with, or we have profitable, and then we take it. And all the, like, I think it's currently ARM and also RISC-V has some quite ugly code in the back end to try to factor in all these ISA details like throughput, latency, and whatever. In my experience with x86, it's mostly garbage in, garbage out. So it's what x86 does, like pick the largest working vector mode is usually good. And you hardly can do better. But x86 ISA is also quite symmetric, so we don't have the variable length ISA with different restrictions compared to the not variable length one, but we have the different sizes and the issue that some implementations have like split data paths and pretend to do larger vectors, but internally like split it into two. And the problem that ARM has anyway, like for the mobile phone SoCs, that you have two kinds of cores in your SoC, and one is slow and one is fast. You have that. We have that with x86 as well now. So that's of course always difficult. But my idea is when you want vectorization, you want to tune for the fast core, because if you want to be fast, you're going hopefully to be scheduled to the fast core.
Yeah, that's what we do too. We schedule for the big core.
No more questions? I think we still have time left.
Well,
7 minutes.
Yeah, you have some exercise, right? Like
Have you want to talk about something? Backup topic.
Did I write that?
Yeah, that's your backup.
No, I mean, did I write backup the slide?
No, that's my my title, but you put in the data.
Yeah, okay. So yeah, that's like a pretty typical example of X264, but it's reduced like that, so that it's barely recognizable anymore. So that's in SATD, that's like the hardest loop in X264. The second loop actually performs like some Hadamard transformation, but the crux of the issue is actually this one. So right now, on our 512-bit vector architecture, this is vectorized as 4 individual vectors. And what we'd like to do is vectorize it as one 512-bit vector, at least on our microarchitecture. And there are now 2 options to approach this problem. One is like straightforward, unroll it 4 times, because the loop only loops 4 times, and then have the vectorizer only see the unrolled loop, let SLP do its thing, and then we're there, basically. So the issue then just is, when is this really useful? And right now, I did some proof of concept implementation, unrolled it in, I don't know, IV Canon or somewhere early on, and it works for our core. At least it used to work, but it's possibly not profitable for 256-bit architectures because the original loop vectorization was nicer. So there's, like, if we force unroll it before, we need to be really sure to do the right thing, or in the end, have some kind of proper cost comparison between the original loop vectorization and the SLP vectorization later on. And that's, well, not going to happen right now, I guess.
So the actual issue with loop vectorization of that loop is that even when we have like the perfect vectorization factor of 4,
Yeah.
our data reference analysis doesn't realize that with that vectorization factor, the accesses are continuous.
Yeah.
So we only have to fix that.
Like
then
the original loop
magic
is more
happens
complicated.
and you
so-
get fast code.
Yeah.
Oh, yeah, yes, it's probably a very easy hack, which is why I didn't do it for the last 20 years, right? But so that's the underlying issue.
Yeah.
I mean, to us it looks quite natural, but to the vectorizer it's basically an access with very many gaps on the outside, right? And on the right side, I do remember it's a 4-element array, right? So
Yeah.
it's also 4 data streams. So it's basically 4 input and 4 output data streams. And the vectorizer doesn't yet realize that when we unroll by 4, and only when we exactly unroll by 4, we get like continuous accesses.
Yeah, so the gaps are closed.
And maybe LLVM has a very clever paper implemented how they deal with these kind of situations, and we can just implement that. Or we have to come up with something.
No, I think they just force unroll here. So
Yeah, of course.
We are on the rules before vectorization, so.
yeah, always. If it's possible, then they just do it. And
Okay.
like,
I mean, the
And-
alternative thing you could do is try to do the cross-linear loop vect and reject it, and then it'll get
yes,
on the-
Yeah.
ideally you could reject
That's-
it,
I-
but like-
that's what happens on x86. At least it did at some point. So
Yeah.
we think, well, it's not profitable to loop vectorize it. Then we unroll it, and then it gets.
so
perfectly
the
vectorized.
like underlying issue on our microarchitecture is that it used to be profitable before the hardware designers did some changes, and now it's not anymore. So it's also like you're right at the cusp of being profitable or not profitable, because like when you vectorize with a large vector length, the code becomes very dense. You need like 2 permutes or so to, like for the original loop, not for that one. And like once code gets dense, it's always tricky to get it right. And on the other hand, if you just have 4 smaller vectors, you can schedule them all around, just load ahead, and you're more likely to be faster, but maybe not perfect, but faster than a very dense code that might not be ideal or so. So it's really tricky to get that right. And well, so right now, I don't think we have an urgent need to do that at full size, but it would still be good to have the potential in the future, obviously.
Yeah.
So yeah, that's this X264 loop.
There's a question. Oh, great. So we have 2 minutes left for the question.
Oh, sorry, it's not about that.
No. Yeah.
No, there are a bunch of other passes that are sort of complementary or enable vectorization, like the various loop optimizations, like IV ops maybe, or if convert and all of that. Do you think those kind of are in good shape, or like they do what the vectorize needs it to do? Because I know we have IV ops is a bit in the maintainer-wise a bit sorry there because bin
It's
doesn't
also
work on it.
vectorization. So it's
But
only-
are there paths that
yeah.
kind of need to be improved to implement all these vectorizer plans, or are those in okay shape?
So are they in good shape? I mean, let's say they are all in maintenance mode unless somebody figures out some new spec benchmark. So there are going to be some new spec benchmarks somewhere in the next few years, because we get a new spec version. Figures out that we need some enablement transform, then we implement that. Like we have the loop distribution path, which saw a lot of activity when spec 2017 was introduced. We have Richard Senniford added the loop versioning path, which versions for the strides. And we are thinking of enabling versioning for the number of iterations, because there's one benchmark, x264, where that would eventually help. So yeah, we do have quite a bunch of high-level loop optimizations that are supposed to enable vectorization. And we add to them when necessary, but we don't have people actively working on high-level loop optimizations in general. Last question.
Apologies if I missed it, but I was watching the last BOF earlier today, the last Vectorizer BOF from 2024, and you were talking about, in the plans for this year, merging if conversion into the Vectorizer pass. Is that still planned, or is that dead?
So no, I'm pretty sure I didn't promise that for this year.
Okay,
it was on the list of like, well, that's the goal for the future. Like Tamar said, there's the issue that currently the vectorizer can't emit control flow on its own, and it currently also relies on the if conversion to remove if the other thing. And
so that'd be.
So I think we have to wrap up. So thank you for coming, and find us on the hallway.